program. So actually Tomer is a grad student in a theoretical field theory, but as you can see from the talk, he's also used to do this masterpiece. And tell us about continuum driven winds for both of you.
Okay, so thank you very much. And so as I said, regarding what you just said, I'm not an astrophysicist per se, so I'm not sure what exactly I need to say to convince you. And so since this work was published this week, so this is the first talk I'm giving about the subject. And so if there's anything at all that you don't understand, please interrupt me as much as you want. And so the title is Continuum Driven Winds from Rotating Stars, or alternatively, the formation of the Homunculus Nebula and Skirt. This work was done with Shacham, which was also a postdoc here about 12 years ago. And this is the Homunculus Nebula of eta-Carinae. You can see this, what starts up is this gray circle in the middle. And this project was originally thought of to explain this, the formation and the geometry of this Homunculus Nebula. And so I will start by talking about the problem modeling super Eddington stars, which is rather obvious. I will present the way out, continue into presenting and so I hope there's no one blocking the crowd. I will show an approximate analytical model that we constructed to explain this system, and I will show you what we got for free. And so, super Eddington stars. So consider the conditions inside a star. And so we have the gravitational force pulling in, we have a radiative force pushing out, and with the luminous blue variables that we're interested in, the mechanical pressure is completely insignificant. And since we just want a limit on the radiative flux, then we won't take it into account. And so a balance of the forces, where the gravitational force equals the radiative force, or more explicitly written this way, defines the maximum flux, which is known as the Eddington flux. Now, the problems that we would like to address are the following. So during the late 19th century, the great eruption which initially formed that nebula I just showed you, eta-Carinae was shining more than 10 million solar luminosities. And so unless you believe that the star was 500 times the mass of the sun, then it was obviously radiating beyond its Eddington limit.
So what is the Eddington limit?
Well, the Eddington limit is essentially 4 pi r squared times the Eddington flux. And so you see that it depends on the mass. And so the question, what is the Eddington limit of eta-Carinae, is essentially a mass-dependent answer.
So for solar mass.
Yeah, the sun is way lower than its limit.
But the number is for 500 solar mass, it should be about 5 times 10 to the 4th, right? So it's only a little bit super Eddington. It's 10 to the 7th.
So again?
So if it's 500 solar masses, it's about 10 to a few times 10 to the 40 hertz per second. It's the Eddington luminosity created field. And so you were saying it was 10 to the 7th.
It was
solar luminosity.
It was
so it's just moderate.
It was even more than that at the peak.
Yeah, but so it's like a factor of a few times, not 10.
Yes, no one's claiming that it was 10 times the Eddington luminosity at no point. Okay, so and this point essentially explained by the work of Nir Shaviv right here at CITA 12 years ago. And the second problem is that several solar masses were ejected to form the nebula, which has the distinct twin lobe symmetry and the equatorial skirt, and I will talk about, this will be the subject of this project. And so the layout. So let's first address the first problem, which will be essentially a review of Nir's work.
How long was it when the star was shining?
Say again?
How long was the time period?
Roughly 20 years.
Okay.
Roughly 20 years.
20 years.
Yes. And so the question Shaviv asked was, what if the star wasn't really super Eddington? Now, what do I mean by really super Eddington? So recall that the maximum flux behaves like 1 over the opacity. And Nir's idea was, what if the opacity is not the Thomson scattering opacity that we implicitly assumed here? And so Shaviv showed that under certain conditions where the radiative flux dominates substantially over the mechanical pressure, hydrodynamical instabilities will form in the atmosphere, and the density will not be homogeneous. And so these blue bubbles here represent high density regions. And as you can see, the light has absolutely no interest in diffusing through these regions, but rather around them. And this happens at very deep in the atmosphere at high optical depth. And so a bit closer to the surface of the star, there's a critical point where the luminosity times the effective opacity equals the Eddington luminosity times the Thomson opacity. This is the critical point, or the sonic point. And from this point on, the opacity reaches its maximum value of the Thomson opacity. And to look at the bigger picture, if the core of the star is at the bottom of the screen, somewhere here, convection is efficient until a point where the density is too low, and generally the conditions do not favor convection, at which point the hydrodynamical instabilities begin to form, and the gamma, which is the ratio between the luminosity and the Eddington luminosity, effectively is under 1 because the opacity is smaller. And so the light diffuses until the sonic surface, beyond which even the effective opacity is larger than 1, and the winds are accelerated continuously. And so this essentially explains how the star managed to radiate beyond its Eddington limit. So the goal of this work is to explain, one, how could several solar masses be ejected during the eruption. 2, how could the nebula have such a distinct twin lobe geometry, and explain the equatorial skirt. And as you'll see, a very simple model explains all of these features combined, of course, with the large luminosity. And the reason why an analytical model is even necessary is because numerical simulations are not even close to modeling the entire system. And so we take another look at eta-Carinae, and so this equatorial ejection of mass is usually referred to as the skirt, and saying that it has anything to do with the equator of the star is model dependent, but as first glance on this geometry will suggest is that the star is rotating, and its axis of rotation is the same as this nebula. And so this is what I want to explain. And so here I come to winds from rotating super-Eddington stars. And so I will not put you through all the details of the computation. I will just show you the key players and establish notation. And essentially, all we did was to integrate equations, conservation equations. And so we have conservation of momentum, which is the Navier-Stokes equations with the pressure and viscosity neglected. conservation of angular momentum, where phi dot is the rotation of the star, the spin of the star, which we will assume to be constant. We have conservation of mass, and big phi is the mass flux. We have conservation of energy, and we are taking just the divergence term, and I can convince you that this results in complete conservation of energy. And so these are the equations that I would like to integrate conservation of momentum, angular momentum, mass, and energy. And what do we know? Well, the key ingredient here is von Zeipel's theorem. And von Zeipel said a lot of things, but the relevant to this case is that the flux is proportional to the effective gravity. And the caveat is that this is true for a steady state solution. And generalizing Chaville, who found that the mass flux is proportional to the difference between the flux and the Eddington flux, the generalization here is the difference between the flux and the critical flux, where the critical flux takes into account rotation as well. So what do we assume?
What is the effective gravity?
Effective gravity, I mean the gravity, the combined force of the centrifugal force of rotation and the simple gravity. Not taking into account, of course, the radiative force. And so what do we assume? Well, we assume that the latitudinal velocity is negligible in comparison to the radial velocity. At first glance, this seems cooked up, but this turns out to be self-consistent and is essentially the reason, well, one of the two reasons that this model is in fact integrable. And the other assumption is that the star is spherical. Now, it is obviously not spherical. We don't claim that it is spherical, but we're only interested in the gross features of the system. And so by assuming that the star is spherical, whereas it is actually not, we lose accuracy for intermediate angles far from the pole of the equator. And so keep in mind that whatever I say is correct close to the equator and close to the pole, but not in between. And so so this is how the solution looks like. I will not go into the details. I just want to explain the parameters. So essentially this is a 3-parameter solution. The gamma, which is the ratio between the flux and the Eddington flux, omega, which is the ratio between the spin of the star and the critical classical breakup spin, and little m, which is the photon tiring number, which is essentially the mass loss to the wind. I will not get into the detail of the solution. I will say that it obviously reduces to the known solution by walking daily in the case of no rotation. And so this is...
Can I add, I'm sorry. The chi of theta here is the opacity.
Say again?
What? I'm just trying to understand the chi of theta.
The opacity is kappa.
Yeah, okay. So what is chi?
Chi is a unitless function that parameterizes the latitudinal dependence. And it is actually...
So it's from the rotation?
Yeah, it's a result of integration. And so once you take all the 4 conservation equations, impose the 2 assumptions that we made, you reach this solution, or this, I could have just plotted this here, and you want to ask that question, and this would be just another way formula. And so I will just present these results, where this is the velocity, velocity profile of the wind, and this is plotted at infinity. And as you see, this solution has the radial dependence, and I'm showing you the solution at infinity. I will shortly explain why this is generally the case. Now, these dots are the observed values of the nebula observed by Nathan Smith, and which is essentially looking at the homunculus and measuring, observing its size. And this solid line is the wind profile for the model I just showed you for a critical spin. For large omega is 1, and gamma, the ratio between the luminosity and the Eddington luminosity, is roughly 2. Now, the dashed line, I'm not sure if you can see it, is the same model with the same parameters, same gamma, the same mass loss. Just after a few years of mass loss, where the critical spin is now roughly 0.9. So as you can see, this is a fit. This is a one-parameter fit. Essentially, we just selected gamma to produce the velocities here, and these are just, since gamma is of order 1, it's 1.6. You can see that what we're getting at the pole is essentially the escape velocity of the star. Now, why did I claim that the neglecting the latitudinal velocity with respect to the radial velocity, why is it consistent? Well, the wind reaches half of its terminal velocity after traversing just roughly 1/10 of the star's radius. That is more than 5 times closer than the analogous value for line-driven winds. And so even if I were able to construct the same geometry using line-driven winds, diffusion of radiation would have completely destroyed this twin-lobe structure of the homunculus. So that's why it is self-consistent to neglect that twin velocity, and that is also the reason why no one has succeeded in building such a model, because any attempts will just diffuse all the since the pole poling has larger density than the equatorial wind, the radiation will just diffuse sideways and completely destroy the geometry. And so the only model that was able to achieve geometry such as the Homunculus Nebula associated with this model was Nathan Smith. We call it the semi-analytical model, which was just an explosion which assumed certain boundary conditions, but that did not explain the luminosity. And here we explain both. And as I see that people like it here in North America, we get some stuff for free. And what do we get for free? So the most interesting here is what we get. How do we explain that the star is at critical spin? So we assume that the star is roughly between 100 and 150 solar masses. It's not so easy to drive such a monster into critical rotation. So the point is that it's not just how you lost the mass to the wind, but exactly how you lost it. And so at first glance, one would suspect that since you lose angular momentum to the wind, you're going to spin down. But it's not always the case. And so the loss of the angular momentum of the star is the gain of the angular momentum of the wind. So the angular momentum of the star is parameterized by this unitless function called the squared radius of gyration. And it's essentially a function of the mass distribution. And similarly, we define an analogous effective radius of gyration for the wind, which is also a function of the spatial distribution of the mass flux. And after massaging these equations a bit, we get this formula, which we can integrate once we assume that at the top of the main sequence, the radius scales as the square root of the mass, and so we can integrate this equation to get an explicit dependence between the dimensionless spin and the mass of the star. And as you can see, it depends just on the ratio between the radius of gyration of the wind and the radius of gyration of the star. Now, stars, especially heavy ones, usually have radius of gyration, squared radius of gyration equals roughly 0.1. And for a spherically symmetric wind, the radius of gyration is 2/3. For the wind profile I just showed you, it's 2/5. So it's still large. So do stars always spin down? And what we found is that just above the Eddington luminosity, or actually the critical luminosity, to take into account rotation, the equatorial winds fall back. So at the radius, at the surface of the star, it seems as if the winds are going to reach infinity, but the equatorial winds are more sensitive to the mass loss than the pole winds, and at some point they stagnate and fall back. Since they fall back, they take no net angular momentum. And roughly the maximal angle, maximal longitudinal angle at which winds are able to escape to infinity behaves like square root of the photon timing number over the spin. So I wrote here these definitions so it'll be easier to follow. And we also found that the squared radius of gyration behaves like theta max to the power of 4. And so as you can see, for very, very small mass loss, for low mass loss rates, the radius of gyration of the wind will be very, very small. Of course, for spins that are high enough. And for the case of eta-Carinae, what we found is that for the values of mass loss to the wind and initial spin, for values under this line, the spin-up condition is satisfied. And so the star essentially spins itself up just by losing winds, which are concentrated towards the poles. And so now we know how the star spun itself up, and the second question is where did the skirt come from?
But so you're saying because the wind doesn't go to infinity,
Yes, exactly, because locally well, essentially the short version is that the pole doesn't know that the star is rotating. And winds originating from the pole take no net angular momentum because they have very little leverage with respect to the axis of rotation. And so only equatorial winds have, well, the equator itself has a radius of gyration of 1. And so if equatorial mass loss will take as much angular momentum as you can. And once all these winds are unable to escape the star, then they just fall back. The only angular momentum which is taken is the one from winds which originate near the poles. So, figuratively speaking, the star loses more mass than it loses angular momentum. And that's why it spins up. And it doesn't necessarily have to, the real spin, the angular velocity doesn't necessarily have to increase, just the ratio between that and the critical spin. And this is what this figure shows. And so, as you can see, for relatively low values for the critical spin and for low enough values for the mass loss, the star can steadily increase its spin until critical rotation. Okay, so where did the skirt come from? And so,
May I ask, how much is the spin changing? It's changing a lot, right?
it's changing with define a lot.
Well, could you go back? I'm
This is-
just trying to understand. Does
No,
that mean
this is not the spin. This
Yeah.
is a contour of this condition being just exactly saturated.
Okay.
And so for parameters of dimensional spin and mass under this line, the star spins up.
Sure, so, but you're talking about mass loss rates. So the reason I wanted this picture is you're talking about very small mass loss rates. This is only a few tens of years, right? So I would have thought that this would have given you a relatively small spin change.
This is the mass loss to the wind.
Yeah.
And so if the mass, for example, if the star loses 0.003 solar masses per year, and its initial spin was 0.06, then the star is in this region and will continue to spin itself up.
But I think his point is during the outburst, the mass fluctuates a lot.
This has
higher.
nothing to do with the outburst.
Exactly, that's the point. We haven't been clear, you haven't said that.
Well, yeah, I'm just trying to,
Thanks. This has absolutely nothing to do with the outburst, and
Trying
Jerry
to
got.
explain why you had high spin in the beginning.
oh,
Yes,
I see. Okay,
exactly.
So this is integrated over a very long time.
Yes. Well, this isn't integrated. This is just saturating the spin-up condition.
The spin up fact is.
Yes, exactly. And
So that is a question. What was the time scale to spin up? You guys did that.
it depends where did you start from.
Sure. But suppose you started at a low omega and then a low lambda star mass.
Well, assuming the nominal parameters of eta-Carinae, it is not likely that the star started with, it must have started with a spin of beyond, I would say, roughly 0.02. This is, the region here is purely theoretical because the star would have had to begin with a huge mass, which isn't stable. Stars, as far as I know, can be 1,000 solar masses heavy.
What's the omega today? Is it more?
Well, the omega today is, it's model dependent. I can say what my model predicts. It's
No, from
omega.
observations, is there any clue as to what
No one has any idea.
it is?
No one can see the star. No one has any idea what its mass is. These all fits to model dependent.
But we have a clue about the mass, right? It's a border of its own.
Well, that's because if it weren't 100 solar masses, then you would have absolutely no chance of explaining the high luminosity.
Exactly.
Okay, great. By the way, just
But there's another clue, which is it is the most evolved star in that cluster. There are other stars where we can do know the mass may exceed 60 solar masses.
okay. Now you're talking about the chemical composition of the Homunculus Nebula.
No, I'm just talking about the eta-Carinae is the most massive star in Compass 60. Or it's the most evolved star, I should say, in Compass 60.
Well, you don't really know its age. You can assume.
No, you do know because you know the ages of the rest of the stars in the cluster.
Okay, that's an assumption.
No, you're assuming they form at the same time.
Yes, exactly.
And it has an undergone supernova. So it's less than 4 million years old.
Well, it can't be 3 million years old anyway because it will. Its lifetime to begin with can't be more than 3 million years old.
It's around 4, but that's it. Yeah. So that's the point though, right? So you do know some constraints. You know it's the most evolved star in the system. It probably did form somewhat earlier than the other stars, that's why it's the biggest, but it can't be much older. Because the star cluster itself has a very small spread of ages.
It can be much older because it's shining.
That's right. So you've got good constraints on how old.
Yes.
But that's what I'm saying. It does mean it is more massive than the other stars. And the other stars have masses in excess of 60 solar masses.
Well, yes, but if you look at what you're saying has been known to some extent for roughly 30 years, and if you look at the past 30 years, every few years someone comes up with another, argues for another nominal value for the mass of the star. And so we don't know. It can be somewhere between 100 to 200 solar masses.
Right.
And in fact, we have reasons to believe that it was actually more than that.
What is the supernova constraint for 3 million years? What are you saying it has to be?
Once you get above about 100 solar masses, stars all very simple. Which is 4 million years.
Okay, so remember that the basic model for explaining the high luminosity of the star is the hydrodynamical instabilities that occur in the atmosphere. And so consider the instant right after the atmospheric phase condition. And so the opacity drops, and at that instant, the luminosity is larger than the nuclear energy production. And so the star has nothing to do but to contract. Now, locally, this is easily understood by noticing that the outer shell feels a smaller outward force because the opacity is smaller. And now the difference between the luminosity of the eruption and the initial luminosity can be compensated only by radiating the gravitational binding energy. Now, losing mass to the wind during the eruption has nothing to do with that. That doesn't compensate for anything. And so the radiative energy is essentially only due to contraction. And so if we plug this back into the angular momentum conservation equation, right now, not assuming that the radius of the star scales like the square root of the mass, because this has nothing to do with, that has to do with evolution, not with dynamics. And we can see that if we, okay, that didn't come out right. Okay, so we parameterize the gravitational binding energy by G times the mass squared over R times a dimensionless constant B, which a constant B is usually the case. Lambda parameterizes just how large the difference of luminosity was, and TKH is the Kelvin-Helmholtz timescale. So as you can see, from analyzing this equation, if the Kelvin-Helmholtz timescale, Kelvin-Helmholtz time, which should actually be divided by this constant beta, is, if it is large enough, sorry, if it is small enough, which happens when the luminosity is large enough, then the equator will become unbound. And so for a critically rotating n equals 3 pultrode, which we modeled the star this way, large B takes this form, and we find that the equator will be produced at a rate equal to this formula. Note that the condition for the equator being unbound is due to the fact that m dot is defined to be negative. It's the mass loss of the star. So the equation is, the condition is the fact that this term is larger than this. And so if we plug in the parameters for eta-Carinae, we find that the mass of the skirt is roughly 0.1 solar masses. Now note that this plot starts from beta between 0.15 to 0.5, and the reason for that is that for the hydrodynamical instabilities to occur, radiation pressure must dominate over the mechanical pressure, and beyond 0.15, a star can be stable, so it's meaningless to discuss anyway. And we can see that for mass loss rates up to 0.4 solar masses per year, which is the highest assumption for the mass loss during the Great Eruption, we get that the mass of the skirt is around 0.1 solar masses. So this is currently the only available estimation of the mass of the skirt. So to summarize, our model explains essentially all of the features of eta-Carinae, the luminosity of the Great Eruption, the mass of the nebula, and its geometry. Now, at low mass loss rates, we find that the star is able to spin itself up because, as we mentioned, the winds are concentrated enough towards the poles. And I would like to add, this is currently the only known self-spin-up mechanism. And finally, we see that an equatorial ejection of mass is a generic property of rotating super Eddington stars just at the onset of an eruption. So thank you very much. Questions?
So is eta-Carinae binary star?
Ah, that is an excellent, excellent question.
Thank you.
I don't know him by the way. And so I'm just. Okay, can you turn this thing off? No, just the sorry, I'm blinded. Just the projector. No, never mind. Can you open the drawings? Okay, about the binary companion. So about the binary companion. So one could argue that the reason the star is rotating near critical rotation is because of spin-orbit coupling with the companion star, and which is a reasonable assumption because the system has extremely high eccentricities, which are believed to be around 0.9, if more transfer gas. And so we proved a cute little theorem which relates the amount of angular momentum that can be transferred between the orbital angular momentum and the star angular momentum. And since it is about 5 lines to prove, I will just show it to you. And so if the angular momentum of the star, so time derivative equals minus, by the way, how much time do I have? Okay. So the angular momentum of the star, the changes with time, just like minus the angular momentum lost to the orbit, or to the orbit, which is minus the moment plus the time derivative. And we know that for high eccentricity orbits, the periodicity distance stays roughly constant until the eccentricity turns lower than about 0.4. So for high eccentricity orbits, we can assume that the periodicity passage is the periodicity distance is constant. And another thing we know is that spin-orbit coupling is usually generates a force that has a very high dependence on distance. So, for instance, for weak friction levels, the force behaves like the distance to the power of -7. And so we can model the spin-orbit coupling as a pulse during a pedestrian passage. And so the difference in angular momentum is approximated as just what happens during pedestrian passages, which is L dot integrate over the pedestrian passage time. Now, we know that the change in the semi-major axis is due to the loss of orbital energy. Now, the orbital energy is given by minus g and m over 2a. And so the difference, or the change in the semi-major axis is 2a squared over g and m, the loss of energy. Now note that this is not an energy conserving system, but we don't need it to. But what we do know is that the change of energy is just the force, or the work done during pedestrian passages, which is roughly the latitudinal component theta, which approximating it as happening only during pedestrian passages, L dot P, theta dot P, and integral dt. And so, as you know, I'm factoring all the integrals of the pedestrian passage time, factoring them out because I don't know what it is. Actually, I do know, but I don't want to take that into account. And so, I can now argue that at long time scales, the temporal derivatives are just the incremental changes every periscope passage. And so what we have is that A dot over L dot is roughly delta A over delta L, and this is minus 2A squared, the angular velocity of the periostrum, times GMM. And this equation we can integrate, and the interesting is that delta L, which is L computed between time t and time 0, is GMM to theta dot p, A minus 1 computed at t and 0. But note that the only, if we're looking at out spin up, then the semi-major axis must be reduced during these dynamics. And so this is obviously smaller than just the current state of the system at 2 theta dot p, A minus 1 now. And so in order to compute what is the maximum value of angular momentum that could have theoretically passed from the angular momentum of the orbit to the angular momentum of the star, assuming that, of course, the angular momentum is conserved during these interactions, we get this value. And we derive this in another way, but this is sufficient. And if you just look at the state of the system today, and you have these rough estimates of the mass of the star and the semi-major axis, and using these you know the angular velocity during periscope passages, and you can compare this with the angular momentum of the star, which, as I said, was alpha g squared mr squared omega. And you can compare that with the same angular momentum of the star, where omega is taken to be the critical omega, assuming the stellar parameters. And what we found was that this interaction could be responsible for just 5% of the angular momentum of the star. And so an interaction with the binary star could not be held responsible for the high spin of the star unless its radius was an order of magnitude smaller than we think it is now. Currently, the radius of eta-Carinae is assumed to be roughly 150 solar masses. And so unless it is 10, then the interaction with the companion is not the reason why the star is 10. And I'm sorry if I had hijacked your question. If that did not answer it, please ask it again.
So you have asserted that it's binary, essentially, or assuming it's binary.
I'm assuming it's a binary, and
Is it known? I mean, I know people say it could be, but what's the evidence that it is or is not binary?
well, you see the
You see a periodic
you
radiation.
see a periodic. Well, essentially, you see the period of the rotation of the two stars.
Well, you see a period, which interprets rotation. What's the period seen?
Well, essentially, everything we know about the star is mostly due to IR imaging, and I don't know to what extent you trust IR imaging, but there are very distinct peaks of a period that is roughly 5.5 years, and people see that this value is actually decreasing. And so it was more than 5 years a few decades ago. And so that and some phenomenon which can only be explained due to interaction with the companion, and that's how they assume that the companion has roughly 30 solar masses, but these are all speculations, and I don't really want to get into this debate because it's not based on hard data. There were models that tried to explain the geometry of the Homunculus Nebula using interactions between the winds from the eta-Carinae and its companion star. Particularly, CITA tried to argue that that is the only possible way to explain the geometry, but and the reason for that is because, as I previously said, line-driven winds tend to smear out after traversing a few star radii, which is a disease that this model does not suffer from because the winds are accelerated very, very close to the surface of the star. And usually, line-driven winds are modeled by a beta parameter that V over V, the infinity, behaves like 1 minus R over R to some power beta. Then for line-driven winds, this beta is usually a half. And for our model, it's not such a beta relation, it's much more complicated. But if you try to force it to be a beta relation, then beta is roughly 2. And so the winds are accelerated more than 5 times as fast, and therefore the geometry doesn't smear out. And another thing that I didn't want to waste time on, since I didn't know how much time I had, is that as we've shown, the star could not have been rigidly rotating during the Great Eruption because of the time scales involved. And it will take me a longer time to get into that, but what essentially this means is that you can't, there's absolutely no reason to try and build a more complete model where we take into account the ablateness of the star and do a more elaborate analysis of the differential equations, because there are intrinsic dynamical dependencies here which do not factor out. And so there is a need to do a numerical computation, but it is mostly just to see that this solution is in fact stable. But other than that, I believe that we explained all of the gross features of the system. Any more questions?
So basically, you have a prediction saying that all the squared stars should have some sort of skirt at some point. Is that a testable?
No.
Is that a testable thing?
No, that's not what I'm saying. It depends on the parameters of the system, but as you can. So essentially, it depends on this relation here. And so, if the star has very, very little binding energy, it has to contract very, very fast to compensate for the increased luminosity. But you don't know the binding energy of a star just by looking at it. You don't know how which of the polytropic assumptions are valid. You don't know exactly the inhomogeneities of the star. And so there's a lot you don't know. So essentially you don't know large beta. Large beta. And lambda, you could know through observations, but essentially you don't know B, and you don't know the mass loss. Because the mass loss is very, very hard to observe. People still disagree on exactly how much mass the Homunculus Nebula has. Some people say it's 30 solar masses, some people say it's 1. And so our prediction is somewhere in the middle, but whether formation of an equatorial skirt will always happen depends on essentially 2 parameters. It depends on the mass loss, and it depends on large B. Because this will always be positive. Because At the onset of eruptions, the wind is not concentrated towards the pole because it's a high load wind. And so this is essentially the most important parameter that we don't know. Okay, so
Okay, let's get going again.